Okay, so to understand this, we must differentiate data and information. Okay, where data is a pixel of gray level values that correspond to the brightness of a data at a point. So it means that if you have an image, once you capture, so all the your image will be consist of pixel with the gray level values. Okay, so what is this gray levels values? It is a correspond to the brightness of a pixel. There will be no meaning of that particular image. Okay, so this one we call it as data. So once you do the pre-processing, okay, where you will involve maybe restoration, enhancement, okay, and then segmentation, okay. So if your image can be interpreted, okay, from the data for the input to be in a meaningful way. So this image will be an information. Okay, so for the input image, there will be no information. Okay, but if you do the pre-process, okay, where you want to recognize the image, okay, so to identify faces, for example, so it will be information. So data are used to convey information, much like the way the alphabet is used to convey information via words. So information can be application specific, okay? So it depends on the application that you want to solve. So with this, for example, face recognition. So your face will be the information where you want to recognize the faces. So in binary image that contains only text, the necessary information may only involve the text being readable. So if your image, okay, be an information, so means that the binary image that contains only text, okay, where this text will be the necessary information, okay, to be readable. So in medical image, the necessary information may be very minute detail in the image. Okay. So there are two types of image compression method. So this one I already give a introduction. Okay, where you will have two type of image compression. One is lossy and the other one is lossless. So lossless is where no data will be lost, no data loss. So means that what is the input will be the output. So means that if you compress using lossless technique, then you decompress, you will get the same as the original. Okay, so there will be no data loss. The decompressed image is exactly the same as the uncompressed image. Okay, so for this type of category, the compression ratio is not very good. So you cannot go higher. Usually it only between 2:1 and 3:1. Okay, for the complex images. So means that you can only reduce the original size 2 times lower or 3 times lower. But for lossy compression, of course, some image data may be lost, okay? But the compression ratio can reach between 10:1 and 20:1, okay? So 20:1 for the complex image or higher. So this is advantage of lossy compression, where you will get higher compression ratio by using lossy. So means that ratio 10:1, you can reduce the original size 10 times lower compared to the original. So in lossy compression, there is a trade-off between image quality and compression ratio. So this parameter can be manipulated by user during the compression process. Higher compression ratio means less image quality. Okay, so if you apply the lossy compression, you have to think of, okay, in terms of the quality and the compression ratio. If you want your image to be reduced much, okay, but the quality will also lost, so it is not a good technique to be used. So should be trade-off between quality and the compression ratio. So you have to reduce, okay, the compression ratio so that the quality will be retained. So compression algorithms are developed by taking advantage of the redundancy inherent in image data. So how compression ratio been obtained? Okay, how they get the algorithm for the compression. So this is from taking the advantage of the redundancy inherent in image data. So it means that you have to understand well how the image data been organized. So there are three primary types of redundancy found in images. So one is coding, one is interpixel, and psychovisual redundancy. So coding redundancy occur when the data used to represent the image are not utilized in an optimal manner. For example, if you have an image with 8 bits per pixel, so that allows 256 gray level values, but the actual image contains only 16 gray level values, means you only use 8 bits per pixel, okay, but originally you already allocate your image of 8 bit, so 8 bit will be a waste, okay. So this can be reduced to 4 bit. So only 4 bit per pixel are actually needed. So the second redundancy is interpixel, which occurs between adjacent pixels tend to be highly correlated. So highly correlated means if you have a pixel, the adjacent pixels tend to be close to each other. So for example, you have an image. For example, this is an image. Okay, so this is a green color. So for this example, the pixel value for each will be the same. Okay, or it can be similar. So this we call it as high correlated. So means that the adjacent, okay, the surrounding pixel tend to be close each other. Okay, so instead of you encode pixel by pixel, so if you do the compression, so all the green color can be represented as 1 pixel maybe. Okay, so because of the highly correlated, you can compress your image, okay, by representing 1 pixel as the green color. Okay, so for this type of redundancy, so it can be applied to image with which have different objects. Okay, for example, on this image, so the green can consider as one object. Okay, this blue line can consider as one object. So instead of you represent pixel, all the pixel here, maybe you can only present once. Okay, not all will be encoded. So the last one is psychovisual redundancy, refer to the fact that some information is more important to the human visual system than other type of information. Okay, for example, we have only perceived spatial frequency below 50 Hz. Okay, any higher frequency information is of little use to us. So you can only use below 50 Hz. Okay, your image no need to have more than 50 Hz. So that one is more on the human visual system how image can be perceived by our eye. So our eye cannot see, okay, image with high frequency. Okay, so might as well you reduce the size to be below 50 Hz. So the key in image compression algorithm development is to determine the minimal data required to retain the necessary information. Okay, so to retain the necessary information is the important factor to be considered if you apply the image compression algorithm. So this is achieved by taking advantage of the redundancy that exists in the image. So means that any redundant information that is not required can be eliminated to reduce the amount of data used to represent the image. So because of the redundancy, okay, information, so you can eliminate the redundancy so that your image can be reduced. So this is the compression system model, okay, where you have the compressor and you have the decompressor. So compressor means you will compress your image. So once you compress, your image will be saved in your hard disk, or your image will be transferred to another location. Okay, so once the receiver get your image, so you have to apply the decompression, where the input of compress will be decoded using the same as you encode. Okay, and then you do the post processing, and then you will get the decoded image. Okay, so the decoded image depending on the technique that you use. If you use lossless, so decoded image will be the same as the input image. If you use the lossy algorithm, so the decoder image will not be the same as your input image. Okay, so this is the model of the compression, where you have to have the compression. Okay, so once you get the compressed file, when you want to open it back, then you have to do the decompression step. So the compressor can be further breakdown into several stages. Okay, where you do the pre-processing, where you do the data reduction and mapping, and then you apply the encoding. Okay, using the quantization and coding. So the data reduction will reduce the image data by gray level of spatial quantization. Okay, so we already gone through on the spatial quantization, okay, where you want to reduce the number of bits. Okay, so that one automatically you will reduce the image data. So remember, gray level reduction. For example, you have an 8-bit, then you want to reduce to 6-bit, or you want to reduce to 3 bits. Okay, so this gray level reduction so will also reduce the size of the image. Okay, so remember you have original 0 to 7, then you divide, okay, into sub-interval. So any pixel value that falls under this interval will be represented as 0. For this one as 2, for example. Okay, this one as 4. So you have original, you want to reduce to 4-bit. So you will divide so that you only have 1, 2, 3, 4. Okay. So you undergo any image enhancement process if necessary. Okay. Then you will do the mapping. Okay, maps the original image data into another mathematical space where it is easier to compress the data. Okay, so then you do the quantization, takes the potential continuous data from mapping space and put in discrete form. So lastly, you will do the coding, map the discrete data from the quantizer